Question 7. Which option best describes the motion of electrons in a conductor when no current flows through it? The electrons do not move, the electrons steadily drift in one direction, the electrons move around at random, or the electrons move in little circles. So what's the best answer out of these four? I'll tell you right away, it's not A. The electrons in a material are never stationary, unless the material is at about -273 degrees Celsius. The correct answer is that the electrons move around at random. This means that the net charge of electrons moving in each direction is 0. The charge of electrons moving randomly to the right is balanced out by the charge of electrons moving randomly to the left, so that there's no current flowing through the material. Question 8. Which option best describes the motions of an electron in a conductor when a steady current flows through it? Do they steadily drift in one direction? Do they move about at random? Do they move very quickly in straight lines? Or do they move back and forth? So what is it? A little while ago you might have thought that the electrons move very quickly in straight lines, the direction opposite to the current. But in fact that's not the case. There is a net motion of charge in one direction, but the electrons themselves don't move very quickly. Our correct answer then is that the electrons steadily drift in one direction. They almost move around at random, but there's just a tiny sort of bias in moving in one particular direction, and that will be the direction that the electric current ends up flowing. Question 9. A charge of 1 millicoulomb, so that's 1,000th of a coulomb, moves across a circuit component. This requires 0.1 millijoules of energy. What is the voltage across the component? Can you remember our equation for voltage in terms of energy and charge? It looks something like this. V equals W, that's energy, over Q. So if it takes 0.1 millijoules in order to move the charge across, then that's the work that we use. Q is the charge, just the 1 millicoulomb. So substituting in those numbers, we have 10 to the minus 4 over 10 to the minus 3, which gives us an answer of 10 volts. Question 10. What is the potential energy of an electron in a circuit at the negative terminal of a 12-volt power supply? So let's think about this for a moment. We have two terminals, a negative and positive, with 12 volts, and the electron is at the negative terminal of the 12-volt power supply. That means as soon as we let the electron go, it's going to start drifting around the circuit. Quite slowly, but it'll get around in the end, right? So we want to figure out how much potential energy it has when it's over here. So in order to figure this out, we're going to have to use our equation relating voltage and potential energy and charge. So let's start by writing down the equation. W equals QV, right? Simple rearrangement. Substituting Q, the charge of an electron, and V, the voltage of the power supply, we get a measure of the potential energy of that electron. So charge of the electron times 12 gives us 1.92 times 10 to the minus 18 joules. Part B. What is the total potential energy of all the electrons in a terminal, at the terminal, if they have a total charge of 1 coulomb? So this time, instead of using 1.6 times 10 to the minus 19 as the total charge, we're going to be using 1 coulomb worth of electrons. So using the same equation, this time we get 1 times 12, which is 12 joules. So the total potential energy of all the electrons at that particular terminal is 12 joules. So as they move around the circuit, they will lose that 12 joules of energy and radiate away as heat. Part C. What is the energy passing through the circuit every second if 1.5 amps flow through it? So can you figure out how we will solve this? Well, we're going to use something pretty similar to this top thing here, except that amps isn't a measure of charge. It's a measure of charge per time. But that's okay, because we're trying to find the energy per time as well. So the equation we use is something like this. We simply divide both sides of the equation by T. That means that on the right side of the equation, we can use this Q over T to substitute in our I. So the energy over time flowing through the circuit is QV over time, which equals I times V, right? Substituting Q over T for I. So the energy per time is the current times the voltage. And substituting in these numbers, we have 1.5 times 12, which gives us an answer of 18 joules per second, or 18 watts. Remember that 1 joule per second is a measure of power, energy per time, which we can also measure in watts. These units are equivalent. 1 joule per second equals 1 watt. Question 11. If the potential difference across a power supply is 10 kilovolts, that is 10,000 volts, what work is done on a charge of 50 microcoulombs, that is 50 millionths of a coulomb, as it moves between the two terminals of the power supply? So what equation will we use here? Once again, W equals QV. The voltage is 10 kilovolts, very large number, and the charge is 50 microcoulombs, very small number. Substituting this in, we have 5 times 10 to the minus 5, that's 50 times 10 to the minus 6, times the number of volts, 10,000, or 10 to the power 4. Now this gives us an answer of 0.50 joules. So that's the end of the questions. In this section, we've learned a little bit about the movement of the electrons in a material, as well as the energy of the electrons as they pass through a voltage.